Hello students, welcome back. Previously we studied binary operations, both a theory and computation. Now we're going to use it as a main tool to discuss the overall preview, of the entire abstract algebra. We're going to study these kind of algebraic structures mostly. Groups, rings, fields, vector spaces, modules, and algebra. And are there any more? Probably not. First, 2/3 of abstract algebra 1 will be on group theory. So that's the most important for our purpose right now. And the next 1/3 will be on ring theory. Now, fields theory will be covered in abstract algebra 2, but you still have to know what a field is because some aspects will be used in abstract algebra 1 as well. Vector space, on the other hand, is a topic for linear algebra, so we don't really deal with it here in abstract algebra 1 or 2. A little bit in abstract algebra 2, but not very much. Module and algebra, those are a little bit more advanced topics, and they're going to be covered in abstract algebra 2, or maybe not even that. It depends. Okay, the simplest and the most important is the group. So let's talk about it. A group is a non-empty set along with an algebraic operation star that satisfies these conditions, G1, G2, and G3. Associativity, identity, and inverse. Some groups satisfy an additional condition, the commutativity. A group that satisfies this another property here is called a commutative group or an abelian group. And the groups that satisfy only these three, those are non-abelian. Here's some examples. Set of all real numbers under addition. Set of all integers under addition. Let's see. Associativity, yes, of course. Identity, 0. Inverse, negative x. Okay, because we have inverse, the subtraction is also well defined. Now, how about multiplicative groups? The set of all positive rational numbers under multiplication, the set of all non-zero rational numbers under multiplication. Let's see, associativity of multiplication, yeah, okay, it works. Identity is 1, and that's a rational number, so okay, that's good. And inverse, 1 over x, okay, that works too. So we have inverse. So inverse of multiplication. So division is also well defined for these. Not for these. Excuse me, for this one, yes, but not for this. But for rationals, yes. Some additional example. Okay, all right. How about some polynomials? The set of all polynomials with real coefficient under the polynomial addition. Yes, we have all these. Associativity, of course. Identity is a constant polynomial, 0. And inverse, negative of p of x. How about this? Matrices with matrix addition. Okay, they all fit. But then again, all these examples are abelian. Can you think of some non-abelian example? Well, let's start from matrices. Matrix addition, that's abelian, commutative, so let's consider matrix multiplication. But that's going to be a bit tricky because number one, multiplication has to be well defined all along, so let's begin with square matrices n by n, but also we have to have inverse. So let's consider invertible matrices only. So I and N, so invertible matrices only with real entries. Then we're going to get a non-abelian group under the matrix multiplication. Here's another example, the script bxx. So x is a set, and it can be anything, but usually it's going to be sufficiently large. It's not like a set of one element or something. That's too simple. If you have something like 5 elements or 10 elements, okay, that's going to be sufficient. Infinitely many elements, that's even better. In any case, let's consider the set of all bijections from x to x. If you consider script f and set of all functions, yes, you can still consider composition, but you don't get inverse in general. So let's consider one-to-one onto functions, just bijections only, then we have inverse functions, so we can consider composition and inverse. That's an example of a non-abelian group too. Okay, so much for groups. Do you have enough time for rings? Probably not. Let's do only first half of it. A ring is a non-empty set together with two operations, addition and multiplication, and under the addition, it forms an abelian group. Associativity, additive identity, additive inverse, and finally commutativity of addition. We have all those. So it's an abelian group with respect to the addition. Now, as for the multiplication, we only have one property here, the associativity. That's it. We do not consider the multiplicative identity or multiplicative inverse. You see, in order to get a group, we need 1, 2, 3. We have one, the associativity of multiplication, but this one, no in general, and this one, absolutely not. And not this one either in general. So we only have associativity for multiplication here. And as for the distributivity, those are there to connect these two operations, addition and multiplication. So they are related like this, and it's not a standalone property for addition nor for multiplication. You have to put these two together. And by the way, we have to have these left and right distributivity in general because we do not have commutativity of multiplication. So left multiplication and right multiplication are two different operations. They're not the same. So we have to have left distributivity and right distributivity as two separate properties. If you have all these, then we say it's a ring. Can you think of an example like that? Oh, I don't know. Can you think of an example that satisfies all these and a heck of a lot more? That's much easier, like integers. If you have integers, then we have both addition and multiplication. No division, but that's okay. We only need addition and multiplication. Subtraction, we can create subtraction because we have additive inverse, so subtraction, yes. But no division because we don't have that property for the addition. For the multiplication, excuse me. For multiplication, we have only one property here. That's the associativity. Now, by including some more, we can get stronger and stronger rings. By adding this condition, by including this condition, I'll try to avoid the term add because addition is used for these already. By including one more, the commutativity of multiplication, we're going to get a little bit special ring. And if that happens, we say that's a commutative ring. The set of integers, that's an example of commutative ring because multiplication is commutative there. Matrices, for example, that's non-commutative ring. We have addition and multiplication and all, but the multiplication is not commutative if you have square matrices. Next, ring with unity. That can be a bit trickier, but here we go. You see, in order to have a multiplicative group, let's go back to the condition of group. You see, this condition here, commutativity, this one, that one's actually a little bit different. Something else that was included later on. As for the groups, we start with associativity, identity, and then we have to go toward inverse. Let's see, associativity of multiplication, it's there. It's there, I highlighted in bold. Commutativity for some rings, but identity for multiplication, not always. For some rings, yes. By the way, we should not have x equal to 0 because we have to remove 0 from the consideration because you will end up proving that 0 times something is always 0. As a matter of fact, we'll rigorously prove it when we get to the ring theory. Anyway, so we have to exclude 0, then we can consider the multiplicative identity. But we want to avoid confusion because the term identity was already taken. So we call it the unity. So unity and multiplicative identity mean the same thing. So ring with unity means we have associativity and multiplicative identity for multiplication. Still, we have one more to go to form a group. So that kind of thing is a ring, commutative ring, and ring with unity. One more. There's still one more. Sorry. Integral domain. An integral domain is a commutative ring with unity, so we have these two. And then in addition, we have another property. No zero divisor. A times b is 0, then either a is 0 or b is 0. There's no way I'm going to get a 0 by multiplying two non-zero numbers. If that's true, then that ring is called an integral domain. Can you think of that example? Well, set of integers, yes, that's certainly good. Integer times integer is 0, then one of those integers should be 0. So, and then also is commutative and it has unity 1. It all fits. Matrices, let's see, not commutative. It has unity, identity matrix, yes. Zero divisor, it'll fail, no. But there's a very, very useful example. The set of polynomials with real coefficients. They form an integral domain, and that's very, very useful in this kind of computation. How do you solve a quadratic equation like this? Factor right hand side is equal to 0, and we use this property. Blue times green is equal to 0. So either blue is 0 or green is 0. We just use the no divisor property. Consequently, we get either blue solution or green solution. That kind of thing is for integral domains. So we went through a lot of rings, general rings, commutative rings, rings with unity, and finally, integral domain. We'll come back and discuss a little bit more about rings